What is a transformation of a function? We start with a given function, and then we compose it with some other function, and you get a new function. That new function is a transformed version of the original function. In what follows, we are going to see three basic examples of such transformations, and we are going to compare the graph of the original function and the new function that we get after the composition. Through this comparison, we get a better understanding of how the composition affected the original function. The starting function for our first example is a function f of x, which is equal to 1 minus x squared. We already have seen this function, and recall that the graph is given by this mountain. Here's the horizontal axis, here is the vertical axis. The domain of this function is all real numbers, while the range goes from minus infinity up to the top of the mountain, which is at 1. Our second function involved here is the function g of x, which is by definition a times x, where a is a parameter of this function, but in what follows we are going to separate that real number in three cases. We are going to consider first numbers a that are larger than 1, and then numbers that are between 1 and 0, and finally let's consider negative ones. So let's start when a is a positive number and larger than 1. For example, when a is equal to 2. So consider a equals 2 is a representative of what happens in general for a larger than 1. So this is our second function, and our goal now is to compose these two functions, f and g, and we will focus particularly on the following composition, g of f of x, which we describe here in this diagram. So first, as it's written, f starts by acting on x, and then g acts on the answer f of x. You see this here in the diagram. So we start by x, the input of the first function, f then acts on it. So notice x lives on the horizontal axis here. F acts on it, gives us the image of x, which lives on the vertical axis here, which is 1 minus x squared, and 1 minus x squared belongs to the range of f. So it is between minus infinity up to 1. From those numbers, 1 minus x squared, now g acts on that number and transforms it into a times 1 minus x squared. So it multiplies the thing by a, which in this case we consider a to be equal to 2. Graphically, what this means is that, well, the input of g lives on this horizontal axis, and the output, a1 minus x squared, lives on the vertical axis. Now, let's consider some special values for x and see what happens when this machine goes to work. Assume that x is equal to 0. When x is equal to 0, well, 0 is here on the horizontal axis, so it's here, 0. Now f acts on this 0, it gives us 1 minus 0 squared, which is 1, and that is the image here, 1. So it's here. So the coordinates of this point is 0, 1. And now g acts on the output of the function f, giving us 2 times 1. Graphically, what does this mean? Well, looking at this picture, we see this pink line, which is our function 2 times x. And if you set the input here as 1, which is here, 1, the output is 2, which is here, 2. And so we have 1 mapped into 2. This point here on the pink line has coordinates 1, 2. Let's now focus on the composite function and how it maps 0 into 2. On this graph here, we find the original function in pink and the transformed function g of f, so this thing here, in green. So 0 lives on the horizontal axis, here it is, 0, and 0 under the first function is mapped into 1. Okay, this thing is mapped into 1. But under the action of the g of f, the 0 is not mapped into 1, but it's mapped into 2. And so the 0 goes instead up to here. You see? As a result, the top of the mountain now is higher after this transformation. Let's now repeat the same line of reasoning, but for a distinct x. Consider then the value 1f. 1f is mapped into 1 minus 1f squared, which is 3/4. Graphically, the mapping of 1f by f is given as follows. So 1f is here on the horizontal axis, and 3/4, which is 0.75, is here. And so this is the coordinate point with 1f 3/4. Now on this number 3/4 acts g, and g computes 2 times 3/4, which is 3f's. From a graphical perspective, this means that the point 3/4 here is mapped here into 2f's. And finally, from the perspective of the composite function, 1f is mapped into 3f's, and so 0.5 here on the horizontal axis is mapped into this value here. So this is 3f's and this is 1f. Let's compare this mapping with the original one, which is from 1f to 3/4. So 1f up to 3/4 here. 3/4. And you can see again the same result. The point on the mountain now got higher. And this is a general trend for all the values of x between -1 and 1. Under the action of f, they are mapped into these images, the pink line, but under the action of the composite function, they are mapped into the green line, which is twice as high. Notice, however, that those values of exactly x equals -1 and 1, they are mapped under the f function here into 0, and the same thing happens with the composite function, because if you insert here -1, it's mapped to 0, but 2 times 0 is 0 again. So these points are common to both mountains. Finally, for all those x's that live before -1, so in here or here, notice that the images under f are below the ground, so they are negative. And by the action of g, which multiplies those values by 2, they makes them even more negative. So in conclusion, when the function g acts on the images of f, all those images above the ground are stretched upwards, and all those images down are stretched downwards. While the points exactly at the ground, here, they remain invariant under the action of g, because they are zeros. Our analysis so far of this transformation from our mountain function into a larger mountain function rests on the understanding of how each one of these intervening functions behave. Moreover, we also chose some values of x, some particular values, and then some calculations to get a rough idea of how things transform, and then generalize that thing for all the other values. Now, from this, we can also guess what would happen if our parameter a was not 2, so a number above 1, but was instead a number between 0 and 1. By multiplying all images of the f function by a number between 0 and 1, all those values are compressed. And so our original mountain becomes a smaller one. But what would happen if the parameter was now negative? For that, let's look more closely at negative numbers. Because negative numbers, let me write it, well, if a is below 0, it's a negative, for example, -2, or -3, or minus something, well, it means that a can be written by -1 times the positive part of a. So -2 means -1 times 2, and 2 is a positive number. -10 is -1 times 10. And from this alone, we can understand the implications of a negative parameter. So our function f of x, which is equal to 1 minus x squared, is now transformed into g of f of x, which is essentially a 1 minus x squared. But since this is negative, we can write it as minus 1 times the positive part of that a times 1 minus x squared. But now look closely at this formula. We can see exactly that this thing, this transformation that happens here from the original function times something, requires exactly the kind of analysis that we just did when the parameter a was positive. The only thing that is new is the multiplication by minus 1, but we can understand what such a multiplication would entail. Looking at this picture, we have here the mountain 1 minus x squared, and in pink we have minus 1 minus x squared. Notice that every single time that we have a positive image, well, after multiplying by minus 1, you get a negative one. So it flips. If you have a positive one, it becomes negative. Here, it flips. And then it flips. And so, graphically, multiplying any function by minus 1 or transforming it by multiplying by minus 1 just flips through the horizontal axis. As a consequence, these kinds of transformations with negative parameters a, it is just a combination of what we just saw when a was positive, with the additional effect of flipping the thing through the horizontal axis. Let's now move on to the next transformation.